Alors, bonsoir tout le monde. Je voudrais premièrement remercier de cette occasion à vous présenter ce projet de Mado, qui est une collaboration de l'Université McGill et ETS. Et je suis désolé, je n'ai jamais présenté en français, alors peut-être je vais changer en anglais pour la présentation. Okay, so this project is a 5-year collaborative project which is already running since April. And within this project, there are 3 areas, and I'm not the project lead. I'm making this presentation for Professor Michael Kokolaras, who is the project lead. He is a professor of mechanical engineering, working in the area of multidisciplinary optimization. Professor Hani Mustafa is the local ETS contact who is working on aeroderivative gas turbines. And I myself, I'm the odd one out, because I'm working in software engineering. And in particular in this project, I'm working in software tool integration aspects. But it's already imprecise because I think most of the team who is working on that consists of 9 graduate students, both from mechanical engineering and software engineering. So this is quite a multidisciplinary project from day one. At Siemens site, we are collaborating with people in Siemens Montreal. Martin Staniszewski is the project manager. But then we are also collaborating with people from Siemens Orlando. Frederic Villeneuve, who is head of digital innovation, Jose Valenzuela de Rio, the product owner, and Matthew Harrison for product development manager. And that's roughly the project setup. Technically, I know how many of you what is an aeroderivative gas turbine? One, okay, so I guess for those who know, I think you know better than I do, but at least I can tell what I learned is that so these aeroderivative gas turbines, or shortly AGTs, are lightweight, so gas turbines for energy generation, which is up to 100 megawatts, and effectively they are adaptations of turbines used in aircrafts. Why do they do this? Because, I mean, there is inherent complexity in the state of practice of AGT design with very fragmented design processes and so on, but they want to rely upon 3 specific aspects of turbines used in aircrafts, which means that they are efficient, they are reliable, and they are flexible. So you can switch on and off them on a frequent basis. And that's the idea, and that's how they, in general, want to improve on slow design cycles and reliance upon only historical data. So generally the goal of this DMADO project, which is even more difficult to pronounce than the EMADO, is to design better gas turbines with 3 specific business goals in mind: reducing the time of design, improving quality, and also reducing costs. And Siemens wishes to achieve this by providing a next-generation design platform which facilitates collaboration between various engineers and heterogeneous teams at Siemens. It should also integrate all kinds of gas turbine components and disciplines, and also covering full life cycle, starting from requirements to field data. And within this project, we are mostly touching upon 2 specific areas, so design platforms and design tools. The overall idea, or the overall view, is that a digital platform is designed or is developed which should cover the traditional aspects of the technical activities being carried out at Siemens, like controls, performance, compressor, design and quality, combustion and turbine. So the outer rim or outer circle is about the gas turbines, AGTs. The inner circle are centered around the main scope of the DiMado project, which is the digital platform, multidisciplinary optimization, and also parametric design. The key scope of this project is centered around these three ideas. For the digital platform, we are planning to incorporate and exploit machine learning techniques as well as change-driven computations in the tool chain, and also coming up with a process-driven software tool integration for collaborative analysis and design. On the multidisciplinary design optimization part, the key focus is to provide hierarchical and non-hierarchical coordination for executing a distributed optimization process, and also to try to quantify different sorts of uncertainties for optimization. And then the most, let's say, technical part is related to component parametric design and integration, which should enhance the design for additive manufacturing, and also to enhance analysis and design of rotating as well as static components. And now in the remaining few minutes of the talk, I would like to give a brief insight to each of the three topics about some ongoing work. I start with digital platform, which is probably the easiest for me because this is my area. Within the project, so within the Siemens project, Siemens is aiming for three key components with respect to the software engineering aspect of a integrated digital platform. One is to have standardized design processes across different organizations, and which is traceable from day one on. They wish to drastically reduce design time for iterative design processes to more a matter of days or weeks and not matter of a month. And they simultaneously also support multidisciplinary analysis and optimization. A key cornerstone or foundation for that is data management, providing global history of or global design history, so storing different versions of the design instead of throwing them away right after completion. So including design data, simulation data, and field data, and then try to exploit this data in the future iterations of that design. And here, the general revision cycle imitates cycles which are well known from software engineering, so pulling changes, revising the design, publishing, and then, let's say, merging. And then data and design processes should come together somehow. And since you are using different sort of tools to achieve this vision, those tools have to talk to each other. And this is the third cornerstone related to process-driven tool integration. Instead of interconnecting those tools in an ad hoc way, tool integration should also be driven by the general design processes, by automated data transformations, taking the output of one tool and providing this automatically as the input of another tool, and also potentially the integrated execution of existing design and simulation tools in order to compare different design variants. If you take, if I may use an analogy, as I'm not allowed to show you the real tool used within Siemens, but you can think about business workflows. How many of you have heard about business workflows in other designs? So if you are applying for a loan application at a bank, the actual steps that a clerk has to carry out for judging your process or judging your application is typically captured by a business process, which consists of things called activities, data flow. So you receive a message from your manager, and then you have to act something. You have different elements in these visual models called control flows. messages, data flow, which specifies the data coming in and coming out of these activities, and so on. But why do I tell you all of this? Because essentially this is the analogy how we plan to interconnect different sort of design tools with each other. So each activity may represent a design or analysis step carried out along a process by a specific tool. And then data flow would represent you the inputs and output models of that tool, which are stored in some model repository, Siemens Teamcenter or similar. Control flows may capture you different design iterations. And then messages or notifications can enhance collaboration by change management and connecting them to project management tools. That's the general idea over there. So you can think about a very related graphical notation for the different tools, different changes, input and output models, and driving tool integration scenarios on the software level. Next, multidisciplinary design optimization. Here the challenge is that you need to meet different sorts of design constraints, which, even if you handle them separately, are challenging enough, but you have to handle them simultaneously. So you have to handle them at the same time. And of course, they may be contradicting to each other. If you wish to improve accuracy, then you need to carry out a related set of analysis. In order to, if you are increasing the number of dimensions, some of those analyses may become too complex or infeasible to execute within a given time frame. So there's lots of interrelated or strongly interrelated parameters which you need to incorporate at the same time by something that's called a design space exploration. So design space exploration is about exploring and assessing different designs like multi-fidelity model management and using robust optimization algorithms also in order to model and quantify uncertainty propagation. So what is the effect? So the analysis techniques and optimization techniques are interrelated to each other. What you learn from stress analysis can be used and exploited in dynamic analysis, which then in turn goes to aerodynamic and cooling analysis, and so on and so on. So instead of separated analysis and optimization steps, all of this is carried out in a coordinated way using hierarchical and non-hierarchical techniques and a distributed setting. Last but not least, component parametric design and integration is related to the AGTs, the core AGTs themselves, and this is the focal area of Professor Hani Mustafa. Within the project, we plan to cover all critical components, including rotating components and static components as well. And the specific focus will be on designing for additive manufacturing, so like coming up with new design processes using 3D printing for additive manufacturing or the like, and also continuously evaluate engine performance like trend characteristics, correlations for cost and weights or similar. What we get afterwards are, let's say, as part of the design are trends or trade-offs between different aspects, which are then evaluated by the engineers to make decisions on which design choices should actually be constructed physically, all the other remain in a virtual or simulated way. I think that's all I wanted to say about the project. Thanks for your kind attention, and I'm there to address at least the software engineering parts of questions. Thanks so much.